Hi everybody. In this lesson, I'm going to continue to talk to you about some of the things we worked on last week, which was summarizing numeric variables. And what we did was we started by using the describe function in the psych package to describe variables and measures of central tendencies. And that function told us about things like measures of dispersion or variability and some measures of central tendency. So I'm just going to use the describe function to refresh our memories. So just make sure that you have the psych package required. Um, so, um, yep, it's required here. So we're in good shape. So let's take a look at the age of patients. I think that we'll start with that. And this is just using the script that we used from last time. And we're going to type in age. And we're going to run this. And we will see that we have 155 observations. Now we had 161 if we click this, you'll see observations for the entire data set. So we are missing data on age on 6 patients, but we can see that the average age of patients is 76.13 with a standard deviation of 7.3. So that means, again, on average, patients varied from the mean on average by 7.3 years. And then we see that the median age is very close to the average. It's a little bit lower of 75.5. By the way, if you have a perfectly normally distributed variable, meaning it looks like the bell curve that you can imagine, that's called a normal distribution, then the mean and the median and the mode is the most common observation, are all the same. So when we see the mean and the median the same or very close to it, it gives us a sense that our data may be normally distributed. We also see that the minimum age of patients in our sample is 64.46 and the oldest patient is 100. The range is actually the difference between the minimum and the maximum. Now, normally you don't report the actual range because a range of 35.54 isn't that helpful because it doesn't tell you the high and the low. Normally we will say that the data ranges from 64.46 to 100. So let's, now we can just refresh our memories, do a histogram of age. So I'm going to put in age. And the X label is years, because that's the age of patients in years. And then we're going to do patient age. Oops. And then if we run this, I want to bring this up to where you can see it. Now we see, and again, you can change the size of this pane to show more gradations. Notice that our y-axis, here we have 0, 20, and 40, but when we stretch this out, it evens out. So you can even, after creating most graphs, adjust the size of it. So we do see it's not exactly normally distributed. It is skewed towards the lower ages, except for, we have very few patients in the 60 to 65 group. Notice that for each of these 10-year age ranges, there's 2 bars. So this would be 60 to 65, 65 to 70, 70 to 75, and so on. You can put in more bars, which, if you want, but they are R will automatically optimize the number of bins that you have. That these are not bars. Again, these are bins because they, and it shows the continuous nature of age because they touch each other. So I just wanted to expand on what we did last week, by showing you a box plot. This is a different way of showing a distribution. And it doesn't generally matter which one you use. Sometimes it's helpful to use one versus the other, but we'll talk about that in a moment. So the command that you want to use for a box plot is simply box plot and age. And we can annotate it later, but for now, let's just run it. And this is a box plot. So the size of the actual box shows the middle 50% of the data. It is the 25th percentile is the bottom of the box. The top of the box is the 75th percentile. And the dark line in the middle is the 50th percentile. And the 50th percentile is the median value. So we know by looking at the describe function that this median line is at 75.5. And the bottom of these are called whiskers. The line at the bottom shows the lowest value that is not considered an outlier. The top one is the maximum value that is not considered an outlier. And this is an outlier. So R defines outliers, to just be technical, as this is called the height between the top of the box and the bottom of the box is called the interquartile range. And anything greater than 1.5 times this box is considered an outlier. So here we just have this one value at 100. So this must be the oldest patient that is within 1.5 times the height of this box. So this 100-year-old patient would be considered an outlier in terms of age. So that's box plots. Let's just do this one more with one other variable so you can get another description. And let's take a look at the variable called tcat sum. And that is the sum total of the variables called cats 1 through 6. And your book gives a description of what each of these are. But lower values, each of these items is on a scale from 1 to 3. 3 being most independent and 1 being totally dependent on each of the items in the scale. And they include items that have to do with taking care of oneself, like the ability to feed yourself, wash yourself, go to the bathroom by yourself, and so on. So the variable tcat sum adds each of these up. So the lowest value you could have on each item is a 1. So 1 times 6 of these would be a 6. So the lowest score, the most dependent patients in the sample, would have a tcat sum score of 6, and the most independent would have a score of 18. So let's just take a look. Let's just describe tcat sum, and we can run that. And you can see on average, remember I said the highest possible score was 18. So the average score here is 15.62. So it's a pretty high average. Most of the patients in the sample, even though they're older, are pretty independent. And on average, each patient varies from this mean by 3.75. Notice the median value is the highest. So, most people are scoring an 18 because at least half of them are scoring an 18. The lowest score is a 6. So you do have people that are the least functional, and the maximum is 18. And of course, the range is 18 minus 6, which is 12. So I'm assuming we're going to see a pretty skewed distribution when we do the histogram, because we know that the median value, the middle value, is the highest score possible. So let's take a look at that. And we're going to call this tcat sum. And the X label is going to be, we'll call it total score, because, we don't, that's the unit that we're going to see. and we'll just call this patient ADLs, activities of daily living. And we can run that. And again, based on what we saw from the describe, you have small amounts of people up to most points. We have in the 16 to 17 range. And again, pay attention to the number of bins between each increment. This is really score by score. So, they're not confining too much. So this is sixes. We do have a decent number of people at 6, but then it's really very low. The tallest bar, of course, is the 18s, and the next highest bar are the 17s. So most people are pretty functional. I suspect when we do our box plot, we are going to see some outliers down here, but we will see. I know the box is going to look interesting, and that's why I chose this for you to see. So here we have a box that doesn't have upper whiskers because the top of the box is, it's the top of the range because you can't go higher than 18. It is the 75th percentile and it is the 50th percentile as well. So there's nothing wrong with the box. It just is like this because, that distribution is so skewed towards the upper ranges. The bottom of the box is like around 14. Again, notice we have some issues with this. We can try to make this a little bit bigger. I don't think I can do this. I'm working on my smaller machine here, but we could get those gradations a little bit better probably if we tried to. Notice that this is an outlier. Even though our box is pretty tall, that those 6s are considered outliers in that distribution, and that is because it's way lower than most of our data, which is hovers in the 14 to 18 range. So I hope this was helpful to you. I hope you enjoyed this, and I hope this is a nice clear recording.